Welcome everybody on the virtual world. Thank you for joining us. Again, I just want to mention about his participation in the diversity, equity, and belonging activities. He's leading a thorough going through everything that American Statistical Association does from the anti-racist angle and be an anti-racist organization. Again, I mentioned this morning. I can share a lot of stories about him because we spent a lot of time together. But he has 1 hour, so let me start telling about him. So I'm going to stay away from that. Let me turn things to Ron Wasserstein.
And by the way, just so that there's no confusion, the Mount Baldy joke was mine. As I was driving here, I said, "Oh, look, welcome to California. They've gotten me covered." So I'm also going to be a little more anchored today instead of wandering around like I might, because I do want to be fair to our online participants. I'm grateful for all of you who are joining online. So I want you to imagine a really amazing car. Okay, so it's probably not Marty McFly's DeLorean for most of you, but this is an impactful car for me. But imagine a truly remarkable vehicle, the most amazing car ever. Beautiful car, runs in violation laws of physics, will run for 3 days on a rechargeable 9-volt battery, doesn't need Doc Brown's 1.21 gigawatts from the movie. It's inexpensive to purchase, so everyone can have one. It's accessible to everybody, but turns out to be hard to drive. In fact, people are just wrecking with it all the time. Well, I'm calling this the 100-year test drive of the concept of statistical significance, which I will go through in detail here in a little bit. And what I want to say to begin with is that people have been pointing out the things that we're going to point out here for a long time. So this is D.R. Cox, who is arguably one of the most famous statisticians, passed away earlier this year, well into his 90s. And he wrote, "It's been widely felt, probably for 30 years and more, that significance tests are overemphasized and often misused, and that more emphasis should be put on estimation and prediction." And he wrote that in 1986. So you can do the math. It goes back to at least 1956, and I'll just own up that that's the year of my birth. So for my whole life, and even before, this has been a concern. Here's another quote from back when, in the early 60s. "The null hypothesis of no difference has been judged to be no longer a sound or fruitful basis for statistical investigation. Significance tests do not provide the information that scientists need, and furthermore, they are not the most effective method for analyzing and summarizing the data." And just one more of these from the wonderfully titled "The Earth is Round," be less than 5. What's wrong with null hypothesis significance testing? Well, among other things, it does not tell us what we want to know. And we so much want to know what we want to know that desperation, we nevertheless believe that it does. So at some point, you can't say that the problem is with the operator anymore, that if we just teach the operator better, they'll be more successful at driving. Here we're sticking with my car analogy for a little bit. And there's even research to show this, that in a recent article in the American Statistician, basically Hubbard showed that as the more people write about the dangers and problems with using statistical significance, the more papers there are that go on about it, that use it. Well, okay, so that's correlation and not causation, but the point is that more and more papers are using these things, more and more people are writing about the dangers, and nothing is changing. All right, time to back up then and get everybody on the same page and talk about what a p-value is. So we wrote, and I'll say a bit more about this a little bit later, we wrote a statement of the American Statistical Association on p-values and statistical significance. And we wrote what we thought was a nice informal definition. A p-value is the probability under a specified statistical model that a statistical summary of the data, so it might be the mean difference between two groups, would be equal to or more extreme than its observed value. We thought that was pretty straightforward, but the press said that the definition was about as clear as mud. So we didn't succeed. One of the people who worked with us on this said, well, you know, we could go this route. Said perhaps this is the simplest general definition. You know, well, I bet there are people here who love this measure theoretic approach, but probably most of you it leaves it a little bit cold. So let's not try to define it. Let's just walk through and describe what a p-value is. So we know some things. We have inquisitive minds and we want to know more things. So we design an experiment to help us figure out how to know the more things. Typically, we would then go about collecting some data. We numerically summarize the results, and we try to figure out what we've learned from this process. Well, statisticians love the designing of the experiment part and the numerically summarizing the data part. And so we summarize the data in the simplest example to a number that we call a statistic. We compute a probability from that statistic, and we call that the p-value. That's the p for probability in p-value. And if the p-value is small enough, we then say that it's statistically significant. What makes something small enough? Well, typically, historically, I'll say a bit more about that later. That's 0.05. So let's take a real quick. There is a new treat that was comparing a placebo to compared with a placebo to prove patient health as measured by total kidney volume. Okay. Questions about total kidney volume. Okay, got nothing. It's just an example. But after 1 year, there was a difference in mean total kidney volume, treatment minus placebo, of 97 milliliters approximately. And so you do the calculations. You get a very wide confidence interval that we might come back to a little bit later. But the p-value is computed to be rounding off to be 0.03. Okay, so 0.03 is the number I want you to hold in your head here for a moment. How do we get that? Well, to compute a p-value, the most well-known assumption is that you start by assuming that your treatment doesn't work in this instance, that there's no difference between the treatment and the placebo. What does it mean when you if there's no difference between the treatment and the placebo, and if everything else we have assumed is true, and I wish I had enough time to talk about all those assumptions, but not here this time, then the probability that we would observe the difference that we saw, that's at 97 milliliters, or something even greater, is 0.03. The p-value is like a teenager. That the teenager is misunderstood. Nobody understands me. Well, the p-value is really misunderstood. In fact, there's a lovely paper by Greenland and others that has 24 common misinterpretations of the p-value and why they're problematic. But here are things that happen when someone has a p-value of 0.03. They think that it means that there's only a 3% chance that the placebo was better than the treatment. No, because we assumed that they were equal. There's only a 3% chance of getting the result we did by chance alone. Also not meaningful, really. The probability that the null hypothesis is false is 97%, and ... because like I said, there's a lot more ways to misinterpret it. It's easy to misunderstand. So what can we conclude? If we can't conclude those things I was just showing you, what can we conclude? We could have had really bad luck in our sample, and if we'd done the experiment again, we would have gotten a larger p-value. One or more of our assumptions could have been wrong, including that base assumption that the treatment was no better than the placebo. Could have been the failure of any assumption of the p-value. Okay, so what does it mean? And our p-value is 0.03. And right here, this is the moment where you will realize why Sastry had me come all the way here. This is the point where you see the level of scientific brilliance. That is why I was invited to be here, okay? It's smaller than 0.05, okay? Write that down. 0.03 is smaller than 0.05, and so we call that statistically significant. You can leave now if you want, because that was the really complicated part. All right. Where do we get this idea of it being statistically significant? R.A. Fisher, who one of the certainly the most eminent statistician of the first half of the 20th century, one of the most well-known statisticians, came up with this idea. And to him, that it meant that not what we think of as significant, but it meant that the results should be investigated further, that it was further scrutiny. And by the way, Fisher, but if he had actually a redo button, he would have chosen to use it for this. This was not his best plan. Significant because that's not what significant means to anyone. So let me illustrate this in a few ways. So let's talk about opposites of significant, okay? So insignificant, unimportant, meaningless, suggest to you something in further scrutiny or whatever as the opposite, or we can think about significant as an adjective. So a significant increase. We'd like to have that in our pay. We'd like to not have that in some other things. We definitely don't want a significant increase in gas prices, for example. We have significant events. We even have significant others. We wouldn't say to someone, not if we were trying to have a relationship with them anyway, we wouldn't say to someone, you know, you're almost becoming significant to me. But just not a conversation that we would have, or at least that might be the last conversation we had with that individual. Okay. First thing that pops into your head about this word, hold on to that. Okay, whatever the first thing is that popped into your head about it, hold there. It might have been a creature that can dig up your yard. It might have been a well-placed spy. It might have been a skin blemish. In the College of Natural Sciences, it was probably a unit of measure. That was the first thing that crossed your mind. But the point is that whatever it was, in context, you're never going to misunderstand that. You're not going to think that somebody was thinking about a spy when you were talking about what caused that hole in your yard. Okay, so there's no misunderstanding there. But lots of other words, even in context, are very easy to misunderstand. Now, for the movie buffs among you, this is a reference to the movie The Princess Bride, in which there's a character who keeps using a word in ways that it's clear he doesn't understand what that word means. Now, I know Roberto knows what that word was. Does anybody else know that movie well enough to know what the word was? Inconceivable. He keeps saying, Vicini keeps saying inconceivable right after something has happened. So things happen, it's inconceivable. Things happen, it's inconceivable. Obviously, they weren't inconceivable, right? Well, that's a misuse of the word. And this wonderful article from Scientific American several years ago talks about misuse of words. So for example, the word hypothesis. In science, we have a specific meaning behind hypothesis. We think of a hypothesis as something that we can actually test. We, in common language, it's used to just mean a guess. You know, I have a hypothesis about why your mother doesn't like me, okay? So it's a guess. I don't really know why. Theory is the same way. Theory is something that means something very specific in science, but the title of this article was Just a Theory. And in science, we wouldn't think about something being just a theory, because before it becomes a scientific theory, it goes through a lot of substantiation. And word number 6 among these 7 words was the word significant. It means something specifically to statistics that it doesn't mean anywhere else. And unfortunately, the standard usage is what prevails. All right, I'll illustrate this with something that you probably didn't think I would bring up today, okay? Tinder, but only imagine here that this Tinder is not for relationships between 2 people, but a relationship between a researcher and a research outcome. And as a result of this, research outcomes, 0.03, it's that number we had. And we look at it, and if we like it, and we're interested in, exploring it further, what's the Tinder operation that we want to take here? If we like it, we would swipe right, okay? The problem is that if you're using Tinder and you don't know what the difference between those two things is, and you swipe right when you didn't mean to, that's problematic. So what Fisher meant by a right swipe in the Tinder of p-values is that these are interesting results. We should spend a little more time, maybe repeat the experiment. We might be onto something here, okay? Unfortunately, the actual use of significant is when people find that they've got a significant result, they treat it like this: you tiny, beautiful p-value, you're the result I want to spend the rest of my life with. Let's publish and get grants together. I love you, little p-value. That's a serious misunderstanding of Tinder, but this is exactly what happens with statistical significance. Now, I'm going to illustrate this in another way in a moment, but I want to talk about thresholds for a minute. And the reason is because we're dealing with a threshold here. We're talking typically about a number being less than 0.05 or it not being less than 0.05. So think about sports boundary lines for a minute. So if you play baseball, tennis, soccer, volleyball, or even pickleball, and the ball touches the line, it's still in bounds, right? It's still in play if the ball is on the line. In football and basketball, it's out of play if the ball hits the line. But that's it. Those are rules. They're well specified. Everybody knows what they're supposed to be. You have to have these boundaries to play the game. Okay, if there was no boundaries on a football field and people could just run it any which way they wanted, or just keep running wide left until they ran off the edge of the earth, or whatever the case might be, the game would be very different. So we need boundaries, and they are arbitrary boundaries. Okay, there's nothing magical that made that a football field should be 50 by 100. Okay, that's just not something that occurs in nature. It's an arbitrary boundary, but it's a necessary boundary. You got to have boundaries in order to play the game. P-values are a very different kind of result in a very different kind of boundary. Just like in sports, if the ball is out of bounds versus in bounds, the results are very different, and the game could hinge on it. In science, a value that's less than 0.05 is thought of and treated differently than a value that is greater than 0.05, even though there may not be very much difference in the actual magnitude of those values. It's an arbitrary boundary. The 0.05 was chosen by Fisher largely because of computational convenience. We didn't have computers, we didn't have calculators back when I used to run with Fisher, and so you had to use tables that were very meticulously calculated and so on. So it's an arbitrary boundary, like a sports boundary, but it's not a necessary boundary. The fact that you're on one side of this line or the other is not actually conveying any particularly useful information or anything that's necessarily real in the world about science. So a declaration of statistical significance does not convey anything useful beyond the information that's already in the p-value itself. And it should be a place where we start talking about what our results mean rather than being the ending place for talking about our results. And again, the boundary is arbitrary. It's not a consensus of people putting their heads together and saying, this is a good place to draw the line. And it doesn't mean that something is more true or more real on one side of that line than the other. The problem is that because the outcome of the game depends on which side of the line that you're on, it's very tempting to play the game in such a way that you try to make sure that you stay in bounds and that you treat results that are on one side of the line as being very different than those that are on the other side of the line, even when there's no real reason to do that. So here's a quote that I love from many years ago by Rosnow and Rosenthal. We only wish to emphasize that dichotomous significance testing has no ontological basis. That is, we want to underscore that surely God loves the 0.06 as much as the 0.05, right? So there's no basis in reality for choosing that level of significance. All right, what you're about to see is true. Only the names have been changed to protect the innocent. What you're seeing here are actual quotes from researchers who needed to get their work published. And so they needed to explain, in this case, why their p-value was a little bit bigger than 0.05, but their results are still important, okay? So almost significant, almost attained significance, almost significant tendency, almost became significant, almost, just barely below the level of significance, just beyond significance, almost got there. These people have a little bigger problem because their p-value is a little bit bigger. So a certain trend towards significance, a definite trend, a slight tendency towards significance, a strong trend towards significance. I think you're seeing a trend here in these phrases, right? And the thing to remember is that I don't know, I bet if we discussed, you would have different opinions about how many numbers it takes to constitute a trend. But I'm willing to bet, in spite of our differences of backgrounds, age, gender, experiences, that we can all agree that the number of numbers that you need to establish a trend is larger than one. And here's the p-value is one number, and yet it's a trend. It's a tendency. It's an expected trend. That's the best kind of trend. Approached our criteria of significance, approaching borderline significance, which to me sounds more like a condition than something. Approaching, though not reaching significance. Okay, here are the people who have the biggest problem of all. Their p-values are almost under 0.05. Didn't quite make it. Hovered at a nearly significant level. Ooh, just floating above it, all right? Hovers on the brink, just about, just above, just at, because somehow or another we needed all those, every one of those digits was significant, I'm sure. Just barely statistically significant, so we rounded down and said it's good. Just borderline, there's that condition again. Just escaped significance, got out the door with that lab rat that got away or whatever, and just failed significance. The thing to realize about this is that these are not crazy people. These are us. These are people who do research, and they're constrained by a world that's requiring them, when they try to get something published, to explain why their values, their results, I mean to say, matter, even though they didn't make it under 0.05. So there's a link that, and these slides will be available. You can find plenty of those quotes out there. So I mentioned earlier that the ASA created a statement on p-values and statistical significance in 2016, and we articulated 6 principles, and I would love to spend time on them, but I'm mindful of the time. So I'm going to focus on principle number 3, that scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. And related to that are principles 4 and 5, basically, that if you're going to do inference, you should report everything and be transparent, and that a p-value or statistical significance does not measure the size of an effect or how important a result is. The biggest takeaway statement from the ASA statement on p-value statistical significance is that bright line thinking is bad for science. And by bright line thinking, I mean just what I was talking about earlier, that a result just below 0.05 is materially different somehow than a result just above 0.05. And so in a supplement to this statement, Ken Rothman wrote, scientists have embraced and even avidly pursued meaningless differences solely because they are statistically significant, and have ignored important effects because they fail to pass the screen of statistical significance. And here's where the hurt comes. It's a safe bet that people have suffered or died because scientists and editors, regulators, journalists, and others have used significance tests to interpret results and have consequently failed to identify the most beneficial courses of action. Those are pretty serious words. So many colleagues of mine and me feel like it's time to move on. It's time to pass on the concept of statistically significant. We've tried it for nearly 100 years now. It's just not working out. And so we wrote an editorial that summarizes 43 papers in the American Statistician, all about statistical and scientific inference that we called Moving to a World Beyond 0.05, less than 0.05. And not coincidentally, on the same day that we released that, an article in Nature, scientists rise up against statistical significance. Why? Well, we've already covered most of this, so I'm just going to summarize here. Significance has lost its meaning. What is supposed to be meant by significant isn't what's meant. I showed you that in a number of ways. Talked about how bright lines lead to bizarre behavior. We end up with writing these funny sentences that don't really mean anything. I've already mentioned that decades of talking about this has not accomplished anything. Blaming it on lack of education or something else is not getting us there. And we wrote that a label of statistical significance adds nothing to what is already conveyed by the value of P. In fact, dichotomization of P values actually makes things worse. And one last thing that I haven't covered, but I wanted to run by you very briefly as we move along, is something called the file drawer effect, which is also very much a part of this threshold. The file drawer effect, one way of envisioning this is, let's suppose that you have a treatment that is worthless. Okay, it's no good. It's no better than the placebo. It's not going to make anybody sick, but it's not going to make anybody any more well than taking a placebo either. And so you test that unsuccessful treatment 100 times, and using a 0.05 cutoff, in theory anyway, on average, 5 of those tests are going to come up being statistically significant. So you have a 5% error rate. It's called a type 1 error in statistics. You have a 5% error rate, and those are the things that get published. The other things all get filed away or whatever, even though they might be useful for some purpose. These get published, and now you have a 100% error rate in the literature at that point. Okay, that's one example of the file drawer effect. So let me be clear as we proceed here that we're not advocating getting rid of p-values. That you saw the disclaimer at the start. I'm not speaking for the American Statistical Association. The 2016 statement, the 6 principles that I showed you, that's a statement of the association. Everything I'm talking about today is not an official statement of the ASA. We published it in the ASA journal, but that doesn't make it a statement of the ASA. All right. Now the really important thing is, this is all very nice, but why does it matter? What difference does it really make? Well, I'm going to give you a trivial example that hopefully is a little bit fun, and then something that's much less trivial, okay? You have been sitting a bit. I'm going to give you a chance to stretch here in a moment. And by the way, at any time that you need more drink or food, please go get it, help yourself. As I told the group earlier, like many kinds of things, I'm easier to swallow with food. Okay, so feel free to help yourself. So this is a phenomenon from a few years ago about power posing. It made lots of headlines because the idea was that if you do certain things with your body language to prepare for, say, giving a talk on p-values or whatever, that you can actually improve your confidence and lower your aversion to risk and so on. And was a published article written by serious people, okay? Not a fraud, not somebody trying to pull anything over anybody, but a mistake was made, a kind of a fundamental mistake. But here's the idea, that you change your posture for 2 minutes so that the idea is when you pretend to feel powerful, does it actually make you feel more powerful? And so they found, here are the magic words, statistically significant changes in testosterone and cortisol level in people who used high power poses versus people who use low power poses. And they found that low power posers were more risk averse. So I'm going to show you some high power poses and then just ask you to take a moment to sit in your seat or to stretch or whatever to adopt one of these high power poses just to get you out of your chair for a minute. Okay. So if this is the one you want to do, that's fine. If you prefer something like this, you can jump up to take up this one is actually called the Wonder Woman pose. Okay. So you can do that, or any one of these, looking really, really relaxed in your chair there. So if you don't want a high power pose, you can low power pose. All right. Maybe you're just not feeling it today. Maybe you've already succumbed to the urge to fall asleep during this talk. So this is a low power pose. Okay. This is not something that you hold for 2 minutes. It's supposed to make you more confident. And this just looks sad, honestly. And this is supposed to be the lowest power pose of all. I've never seen anybody sit like that. And I hope I don't. So what went wrong with this? I mean, you might have noticed that TED Talk had 54 million views on it. And I think people are still doing this, okay? Because they didn't see the correction come out. But the problem was that when other people tried to do this, the study didn't reproduce. And this is not surprising in studies that involve human behavior, because we're just complicated, right? It's very hard to measure the things that we do, and it's very easy to get too excited about a new result without giving it a chance to see whether it reproduces. Example, and a big part of the reason it didn't reproduce, that there was a lot of dependence on statistical significance in there. You saw that these things were significant. There were some other things that weren't significant. So Andrew Gelman wrote, these aren't bad scientists or bad people. It's just that the data is noisy. But when you go try to do the experiment again, the noisy data doesn't reproduce. Okay. The world will not come crashing down because we didn't get the power pose right. Okay. Roberto is all in. And so he is, whatever happens the rest of the day, he's going to be more confident and more self-assured, or else he isn't. All right. So this is serious, and you may have read about this. This drug was called aducanumab. When it was being studied, it's now marketed as Aduhelm, and it's a treatment for Alzheimer's disease, a terrible disease for which there is no effective treatment. It's horrible, and people suffer greatly from it. So here's how this story goes. So this drug, an antibody, has been shown to remove amyloid clusters in the brain. And these buildups have been associated with Alzheimer's disease. So there is a relationship that's been found between these clusters and Alzheimer's. But what we don't know is whether breaking those down undoes the effects of Alzheimer's. Okay, we don't know whether that will happen. And no drug has thus far succeeded in reducing the effects of Alzheimer's. Okay, so there isn't anything there. But this drug, some things happened when they tested. So the first thing was that, and I'm sorry, that's too small, so I'll read. Biogen stopped 2 simultaneous clinical trials on the effectiveness of aducanumab in March 2019 after futility analysis indicated the study would not likely demonstrate efficacy. And futility analysis is kind of what it sounds like. It basically says there's not any point in continuing to run this test because it does not appear that we're going to get to a successful demonstration. But because of the nature of the way the data was being collected at places all around the world, data continued to come in, even though the study itself was not continuing. So that all of the data had not been received by the time of the futility analysis. And so for that next 3 months, basically, there were an additional 179 participants in one of the arms of the study and 139 in the others, but completed the full 18 months of follow-up. And this is the source for this story here. And so they did a subset analysis of those with the added in who received the full uninterrupted treatment. And in one of those 2 trials, statistical significance was achieved. And so they argued that, and the effect size was that the higher dose led to 23% less cognitive decline in a placebo after 78 weeks. That sounds pretty good, right? 23% less cognitive decline is good, but probably at least some of you are thinking, those of you who have managed to remain conscious during this entire presentation, a real challenge. You're thinking that, well, how do they measure cognitive decline? And the answer is, it's an assessment that somebody makes on like a 1 to 5 scale. Okay, so it's not a super clear way of measuring this. And the Biogen argued that the difference in the results could be explained by a protocol change. So that's why it worked here, but it didn't work there. But subgroup analyses are not the place for a focus on p-values, and that 23%, which sounds like a lot, might not actually even be clinically significant because of the scale that this stuff was measured on. Well, this happened, and then COVID happened, and the FDA had other things to worry about for a while. Eventually, in the summer before last, FDA approved this drug over the recommendation of its expert committee. So they have an expert panel that looked at this and said, nope. And the people higher up in the FDA said, yep. And why? Well, there's a lot of pressure because nobody has anything that works on this disease. And wouldn't it be great if this worked? But then things really went south. Clinics wouldn't do it because they disagreed with the FDA's approval of it. Insurers wouldn't cover it, and so on. So we don't know what happened in there. I'm not an expert, but those people who were on that panel are experts. But here we see what happens, an illustration of what happens when we get focused on this threshold. One study was significant, one study was not significant. And there's so much money involved because Biogen invested millions, billions of dollars, I'm sure, in the development of this. Lots of hopes involved because any of us who have a relative or had a relative who suffered from this would love to see their suffering minimized. But now tests will continue, but it's tested sort of in use, and it may be years before we actually know whether this worked or not. So these examples just point you to the fact that change is needed in how we think scientifically about statistical significance. And I love this, this explanation from Steve Goodman. The basic explanation is neither philosophical nor scientific, but sociologic. Everyone uses them, that is p-values. It's the same reason we can use money. When everyone believes in something's value, we can use it for real things. Money for food, and p-values for knowledge claims, publication funding, and promotion. It doesn't matter if the p-value doesn't mean what people think it means. It becomes valuable because of what it buys. So what do we do instead? Well, we have, if we're telling people to stop using thresholds to interpret p-values, what do we do? And we have, I'm going to point you back to this, the special issue of the American Statistician, which is online and open access. I'll talk about a few here, but here's sort of the underlying question. If you think about this, if you think about what it means to move to a world beyond 0.05, this is the question to ask. What if we never had this arbitrary threshold? What if Fisher had not felt the need to come up with 0.05, well, then what would we do, right? What would we do to get a paper published, a grant funded, a drug approved, a policy or business recommendation accepted? What strategies would we use instead? Okay, so my colleagues and I offer very briefly here, and I'm going to skip the detailed explanations, 5 things that we think could fairly easily be done instead of just doing statistical significance or doing it at all. First of all, we could focus on effect sizes and other measures of uncertainty. Skip the whole thing about whether it's significant or not, whether it's 1 asterisk, 2 asterisks, or 3 asterisks, and go right to these. Focus on the substantive implications of those estimates. So what happens often, for example, is that we get a confidence interval, like that one for the total kidney volume medicine that went from like 11 to 190. Well, so what a lot of people would do in that situation is, well, 0 is not in that interval, therefore good, it works. But does it? Is 11 milliliters, does an increase of 11 milliliters in total kidney volume, does that improve the life quality of the individual who's suffering from some sort of condition? I don't know, but that's the question of for people who do know to know the answer to that. And I'm pretty sure that I could guess that there's a big difference between 11 milliliter increase and 190 milliliter increase, and what are the implications of that? But those are the things to think about. And this is what I was trying to get at earlier when I said that 0.05, that significant or not significant should be the starting place for discussion, and instead it's typically the ending place for the discussion. Significant, yay. It was not significant, we're out of luck. All right, some other changes that could be made. Interpret confidence intervals as compatibility intervals. So you're thinking about this in terms of how compatible your data are with the model that you have hypothesized. And I would take more time to give you an example of that. It's in the slides, but I can see that I'm not going to have that much time. When presenting p-values, don't categorize them. Don't say significant or not, highly significant, 1, 2, or 3 asterisks or whatever. Report the p-values. And along with a standard p-value where you assume a null hypothesis of no difference, you could report p-values for other pre-specified hypotheses. For example, you could have a panel of experts decide what a minimum meaningful effect size was. So for the kidney volume thing, maybe it's 50 milliliters, okay? So don't test to see whether you had an increase of 0 milliliters or not, which is what a standard null hypothesis is. Test to see whether you had more than 50 increase. Or you could even, for those of you who are into statistics, you could even do the whole, graph the whole p-value function for alternate hypotheses. And finally, interpret p-values for what they are, as descriptive measures of compatibility with the model, recognizing that the p-value is impacted by all kinds of other things that happen in the process of data analysis. And this one is a little harder, but it's maybe the most fundamental, and that is that we should really be thinking about this from the standpoint of everything that's involved in our experiment, all the things that you do as scientists. What's the prior evidence? How plausible is the mechanism? How plausible is it that standing in a certain position for 2 minutes changes your outlook on life? Can you define a mechanism where that might be happening? And if you can't, then you don't throw away the result, but you ask yourself, do I need to experiment further instead of running and making a TED Talk and getting 50 million views? Think about the study design, the data quality, the costs and benefits. The more novel the finding is, the more scrutiny it should undergo, and other facts that vary by the domain that you're in. Okay, I'm going to take a moment to tell you that, you may not be surprised, but not everybody agrees with the things that I have said, in spite of the extraordinarily convincing arguments that I have made. Kidding, there are the people who think differently. And so I'm going to just briefly outline what some of those other points are. And and I think they're important that you be aware of them. So there's basically four sets of kind of opposing views. And one is that if we get rid of statistical significance, we just throw it open to anarchy. Now we have this nice rule. It's less than 0.05. It's not less than 0.05. And so people have made analogies to the Wild West. And John Ioannidis, who some of you may be familiar with, worried about a state of statistical anarchy arising. Without clear rules, science and policy may rely less on data and evidence and more on subjective opinions and interpretation. So that's a school of thought. Another school of thought is the baby with the bathwater thing, which I have to say is an analogy that I get. Okay, in the whole history of the world, has a baby ever been thrown out with the bathwater? I'm guessing not. But the idea is that that researchers might read the call to abandon statistical significance as abandon statistical methods altogether. So that's a concern that's been expressed, including by a former ASA president. Old music lovers will recognize this, and what this relates to is that people will say, well, why all this focus on p-values and statistical significance? Because there's other statistical methods that have the same problem. And so that's what Benjamini, a very distinguished statistician and scientist, argues, is that other measures, like, say, for example, the Bayes factor, have the same problem. And yep, it's true. Thresholds are thresholds. But the difference is that people haven't been screwing up the Bayes factor for 100 years. And that's been going on with statistical significance. And so then there's the whole idea of, well, what do I do if I have to make a decision? Should I stay or should I go? Well, the argument is that people make is that inferences are unavoidably dichotomous. So we have to have a threshold. So that's basically four categories of arguments expressed in such things as the ASA President's Task Force, where they say that significance testing properly applied and interpreted are important tools that should not be abandoned. So directly the opposite of what I'm saying. And they argue that thresholds are helpful when actions are required. So I'm just going to say this much about those arguments. With regards to the Wild Wild West, do we keep the peace in the Wild Wild West by using a tool that really is not suited for that purpose? That doesn't seem right to me. The baby, as it is, that would be thrown out with the bathwater is about 100 years old now, as I've mentioned already. We know that other methods can be misused, but we know that this method is being misused. And it is true that decisions are sometimes, maybe even often, dichotomous. That is, we have to choose one thing or another. We have to approve the drug or not approve the drug. But that doesn't mean that the evidence is dichotomous. The evidence is most likely, the strength of the evidence is most likely on a continuous scale, and breaking it down into dichotomous choices is problematic. Okay, so we argue that it's time to stop using statistical significance as a metric, and others have written about this. And again, we're not suggesting getting rid of p-values. They're still useful. We just argue that don't use them with a threshold. So thanks, and I guess I even managed to have a few minutes for questions. So if somebody online has a question, will you be able to grab it, Roberta? Okay, thanks.
Okay, so of course, in many ways that you optimize the value, so we use different tests, different analysis, you know, which there's a so
Right.
Inside this.
Yes.
So those are one of the things. But what if factors would be required before they can start an expert to give you detailed, report about how they will do the analysis? What kind of would that be helpful?
It would. And there is a movement for exactly that. That's called pre-registration, that you say in advance, here's what we're going to do, and here's how we're going to do it. And then if things happen that don't allow you to follow that pre-registration, then you have to declare all of that and say what you did instead and why. So that's exactly right. Even without that, if people were transparent about the analyses that they did and made their resources open so that you could bin things differently than they bin them and see whether that changes the p-value or not, because you had access to that information, you could put more trust in that value of p, whether that, as far as you know, they could have just done the one analysis and that's the p-value they got, or as you said, they could have done 50 different analyses and that was the one that was lowest. So pre-registration is out there as something that people can do, and it can be done publicly. Another suggestion that's like that I'll just mention real specifically is getting a publication approved in two parts. The first part is that you submit your experiment and so on before you have any results in there, so that if the reviewers think that your research is being conducted properly, then it doesn't matter whether you get a low p-value or a high p-value, your results are still going to be reported, as long as there isn't anything ridiculous that happens afterwards. And so that removes some of the motivation to cherry pick, like you were saying. Yes, sir. Online.
I'll alternate with our virtual.
Sure.
We have one of our attendees is asking. I don't know.
Okay.
Here we go. The question is this: do you think data science and machine learning methods can be a remedy? These methods aim to pattern seeking, not dichotomies.
Right. So with that, I should have repeated the question the first time. Did they hear you or they're saying it online? So our data science methods an answer to this? They could be. You can make a whole lot of inference mistakes doing prediction, for example, or other kinds of analytics because you don't have a very well designed experiment, or you didn't. There's bias in the type of data that was collected, and so on. So yes and no, because it still requires some careful statistical thinking, and again, not pressing to just decide that your results mean something because they came out of an AI or ML algorithm. Go for it. The file drawer effect. Yeah. Right. So for the online folks, the question was, what about the idea of journals not rejecting papers because of the value of the p-value and whether it be high or low? That kind of institutional change is really what's needed, because right now that we're so far from that. We're so very far from that, even though there's been these discussions now going on for many years. If journals published good experiments, regardless of whether the outcomes or what people hoped they would be, the effect would be amazing. Okay, so people could look at that and see what not to do. They could look at it and see, well, okay, I still think that what you hypothesize is true, but I don't think the way that you went about doing that experiment was really successful, and I'll take a different approach to doing it, or I'll try what you did with some tweaks or whatever. Whereas if that just ends up in the file drawer and it never sees the light of day, then I think science really loses as a result of that. And we really should be able to get to the point where we can publish those kind of things. We have, and this is a Wasserstein approximation, about 4.3 billion journals at this point. It seems like somewhere in there we could be allowing the idea that we don't have to get a statistically significant result to publish.
Forget, I know we're at the top there, but I want to squeeze one.
Sure.
Another question from our virtual attendees, Dr. Wasserstein. The media's role, by definition, requires effort to explain science to the average reader. How can researchers resist media pressure for simplification of their findings?
So that's a great question. And again, it's one of these institutional change sorts of things. Let's talk about real quickly what happens now. What happens now is a researcher at the institution comes up with some amazing results. Well, the university wants some publicity for it. So they hire, or they have on staff already, a science writer who writes up these results and tries to get it out there so everybody can see it. And if it's really interesting in some ways, then the public, then the media takes it and runs with it. So, an example I could have shown you, I kind of wish I had now. There was a study where it was shown that a glass of red wine was at least as good, if not better, than an hour in the gym. Okay, yes. Why wouldn't we wish that to be true? Okay, and there's some of us who are already engaged in that experiment already. Okay, but it turned out that at the end of the day, it was the subjects were rats, and they weren't getting wine. There wasn't a little group of rats having a wine and cheese party or something like that, but they were given a certain amount of resveratrol or something like that. That is a preservative in wines. And then, the rats had significant improvement statistically. The point being that then the people who wrote that didn't say, so stop going to the gym and grab a really good red wine. They just said, here's what. But then it went through this evolutionary process where by the time it got to the media, there were extraordinary headlines about, red wine better than going to the gym and so on. And so what's the solution to that? Well, I guess the solution probably depends more on the hearer than on the writers, because there is so much pressure on publications to say, to write something exciting. These words should be cause red flags to go up for you, and anytime you see them. The words are in a groundbreaking new study. Okay, the thing about breaking ground, if we can stick with that analogy, is that that's the first step towards building a building. You're not you're breaking ground for something over here. It's a performing arts center. You're not ready to go perform Shakespeare in there. I looked over there. It's not quite ready for that yet. But that's what happens with these studies, is they get treated as though the whole building has been built, when actually there's just one study that needs to be followed up on. Okay, you want to come over here, Sastry, so people can hear you, and we're there. Go ahead, so the online folks can hear.
Yeah, for the previous talk, he got a lottery ticket. Even though he convinced us, the chance of winning is so low. But right now we're giving some swags from College of Natural Sciences to remember us by. So
So here it is, right here, the winning Powerball ticket purchased for me.
Just
by
this
Roberto.
morning.
Just in case we split, right?
Yeah, we'll work out the details if you can find me. Okay. All right, so let me open this up.
There's a little surprise in there.
Uh-oh. Yeah.
Participating in this, we appreciate,
Right, some more swag from the College of Natural Sciences. And still, oh, that looks like, so is this a bottle opener?
Yes.
All right, so wine time. Wow, okay, thank you all very much. I'm gonna stop making you watch all this because it just keeps going in here. This is, this one? This is Hermione's bag, apparently. It just, stuff just keeps coming out of it. Oh, wow, now that was fast work. Okay, so this picture was taken this morning and already it's framed. So thank you very much. That's welcome.
Thank you to my colleague Yolanda.
She's back. In to a prominent place for sure.
Thank you for everyone that joined.
Thank you for coming. Yolanda, that's amazing. That's amazing.